Here's our quiz on energy changes associated with ionic and covalent bonding. When we look at ionic bonding, we're kind of thinking Coulomb's law. I mean, now E we're going to refer to as lattice energy instead of maybe in atomic structure where we were thinking about ionization energy, like energy associated with the removal of electrons, which did depend on the degree of attraction between the electrons and the nucleus. And here, technically, E, lattice energy, is energy released when the ions form their bond. Now, we're not going to calculate lattice energy from this equation, but it kind of helps us to think about how much energy is released when certain ions form ionic bonds. Q1 and Q2 are the magnitude of the charge, and then R radius or distance between the ions will refer to the size of the ions. So we still have to kind of think about periodic trends. Which of the following statements concerning lattice energy is false? So one is true. It is often defined as the energy released when an ionic solid forms from its ions, usually ions in their gaseous state. So often lattice energy is referred to as a negative energy released. It's an exothermic value, but it's also then the amount of energy you would have to add to separate the ions. Same quantity of energy, it's just going in the opposite direction. Energy is released when bonds form. Energy has to be absorbed to break the bond. Magnesium chloride has a larger lattice energy than sodium chloride. Yes, it does. Here we're looking at ion charges. That's always the number one thing we think about in terms of lattice energy and ionic bonding. Number one thing, numerator, magnitude of charge. And if I have a plus 2 minus 1, that should be a stronger attraction than a plus 1 minus 1. And so then more energy is released when the magnesium and chlorine ions bond, which would also mean that more energy has to be added to separate magnesium and chlorine ions. If we have the same ion charges, then I look at the size of the atoms. So if I skip the right answer and go to the last choice, magnesium oxide and calcium sulfide both have the same ion charges. Then I look for the smaller ions. I'm looking at R being in the denominator. And so if I want more energy released, I want smaller ions. And so then I can look at trends between magnesium and calcium. Magnesium is smaller, and same would be said about oxygen and sulfur. Oxygen is a smaller ion. Now, obviously, there could be some situations where you might not be able to qualitatively gauge lattice energy, like which shows a stronger attraction. What if I've got different ion charges and like substantially different radii? You're not going to get anything like that on the AP test. That would have to be solved with a calculation because they don't even put this equation in the packet. So you're never going to have to calculate lattice energy from this equation. We're just going to have to use the equation to compare strength of bond or compare lattice energies. And in that case, it's always going to be examples that can be solved qualitatively, kind of like option 2 and option 4 here. Number one thing we think about is magnitude of charge. If there's higher charges, that is automatically the winner. Number 2, if the charges are the same, then I think about radius. And I'm looking for smaller ions that can then pack closer together. Now this question is asking which is false, so it is the third statement. The lattice energy for a solid with a plus 2 minus 2 should be 2 times that of a solid that is plus 1 minus 1. Well, it's for sure not going to be double because I'm going to multiply the charges, and so maybe it would be 4 times. But then if I'm technically going to like quantify lattice energy, I would also need to know the radius, like the distance between the ion centers. And so option 2 and 4 are better statements that I could qualitatively say that one lattice energy is larger than another, but to say that it would be 2 times or 4 times, that I cannot do qualitatively just by looking at charge alone. Then I would need to know the size of the ions as well. All right, now here is a calculation that I could do. Now, this one, obviously, you can use your calculator because the numbers are a little bit funky. Nowadays, if they gave this to you in a multiple choice question, they're just going to round the numbers and they'll say, like, sublimation energy is maybe like 160, and maybe the lattice energy is negative 1000. Or things will be rounded so that they're approximations, and obviously then you could much easily and quickly solve without a calculator. But here, with the numbers still being a little wacky, feel free to plug them in. Okay, so when I am solving for lattice energy, or this one I'm solving for enthalpy of formation, which is like the overall energy change in the formation of 1 mole of lithium fluoride solid. So enthalpy is really just a fancy word for energy. Okay, so there's steps that have to go into play here, and that I need to prepare the fluorine ion and the lithium ion so that eventually then they can bond together. All right, so let's go with the lithium first. So eventually we need to remove an electron to form a lithium plus 1 ion. Technically, ionization energy is measured as energy required to remove an electron from a gaseous atom. Because if you think about the solid, I mean, if I first start adding energy to a solid, it's going to go through a series of phase changes. Then once it's in the gas phase, I can remove the electron if I continue to add energy. So when we put this sublimation energy down, that's to form the lithium atom in the gas phase. So that then the second step, I can use the ionization energy for lithium in the gas phase. So there's my first two steps. I need to prepare the lithium ion. First, we're going to sublime the lithium, turn it into gaseous atoms. That's going to cost me 161 kilojoules. And then once it's in the gas phase, we can remove the electron for another 520 kilojoules per mole, which we do have 1 mole of lithium. And so all of that is endothermic. Going from solid to gas is endothermic. Removing an electron is endothermic. Then even when I start to process the fluorine ion, it starts off endothermic. When we think about electron affinity energy, that is the energy released when an electron is gained to form a negative ion. But it's always measured from the atom being in the gas phase. So I have to take this half a mole of gaseous molecules, F2 molecules, and I need to separate them to form the gaseous fluorine atom. Now here's the one step that sometimes people kind of fumble, and that when I look at the units, electron affinity is kilojoules per mole. There we go. Kilojoules per mole. But in the balanced equation, I only have half a mole. So I'm going to take that half a mole of fluorine molecules, diatomic. We'll break their bonds so that we end up with 1 full mole of fluorine gaseous atoms. But then I take that bond energy and divide by 2. I just need half a mole, so I only need half as much energy. But I'm going to form 1 full mole of the fluorine gaseous atom. Then we can gain the electron, and finally we release energy. The electron affinity is the first step that's exothermic. We'll release 133 kilojoules per mole. Now that I have formed the lithium ion and the fluorine ion in the gas phases, it's time to add them together. So once I join the 2 ions to form the solid lithium fluorine, that energy released is lattice energy. Energy released by the formation of an ionic compound from its gaseous ions. That will always be exothermic. But the whole process is a sum of each individual step. There's a lot going on here. Some steps require energy, some steps release energy. So overall, then we add the energy from each individual step, and we'll find that this reaction does release about 608 kilojoules per mole of lithium fluoride produced. So it's overall exothermic. But once we kind of break down each individual step, the energetics kind of show us that there are parts of this process that are endothermic, but overall, more energy is released in comparison to the amount of energy that was absorbed. Awesome. Question 3. Which of the following compounds contains both ionic and covalent bonds? This is going to be what happens when you have polyatomic ions. Polyatomic ions are all non-metals, and I should say mostly non-metals, and they look like little formulas, and they often involve some kind of covalent bonding. Now, eventually, we'll look more closely at drawing Lewis dot structures, but initially, nitrogen has 5 valence electrons, and maybe you kind of remember drawing these dot structures in first year chem. You would have drawn Lewis dot structures with nitrogen. It's got 5 valence electrons, so usually you made like NH3, where you hooked on the 3 hydrogen, and then the 4th spot was left as the lone pair, which was fine because nitrogen still had an octet. Well, if you're gonna hook on 4 hydrogen, then you got 1 extra electron you got to get rid of. If I hook on that 4th hydrogen and I keep the extra electron, that nitrogen is overloaded. It can only have an octet. And so that's where the +1 charge comes into play on the ammonium ion. If you want to bond nitrogen and 4 hydrogen, you can do it, but you're going to have 1 extra electron that you got to get rid of. And that means somebody's got to take it. And so that's going to be chlorine here. So there will be a transfer of electrons from the nitrogen to the chlorine. Now, in general, often ionic bonds are metal bonded to nonmetal. And in general, covalents are often nonmetals. All nonmetals. Often, that's the quickest way to identify metal, nonmetal. So if I see something metal, like potassium, that's ionic. If I see magnesium, ionic. If I see 2 nonmetals, 99% of the time, that's covalent. The polyatomics are a little bit goofy in that most of the polyatomics themselves are covalent nonmetals bonding together, but they just don't end up being neutral in that if it's a positive ion like ammonium, it's got 1 extra electron. And then what we're going to find soon is some of the negative polyatomics, let's say carbonate, CO3 minus 2. If you want to bond carbon and 3 oxygen, you can do it, but you're going to be short by 2 electrons. If you want to give everybody an octet, which is the whole purpose of bonding, you're going to need 2 more electrons, which then is why we would often bond that to maybe something like calcium that has a +2 charge. Calcium can donate 2, and then I've got this ionic transfer of electrons, but within the carbonate ion, the carbon and the oxygen will share electrons. They're just going to need 2 more electrons in order to give everybody an octet. But in general, ionics have a metal and covalents are all nonmetals. Easy way to identify 99% of ionic and covalent bonds. All right, so then we've got these little energy graphs where the bond length will be at the minimum energy level. Low energy is always more stable. So the bond forms when the energy level is at its lowest. And so if you follow that up, you can estimate the bond length. So somewhere between 50 and 100 picometers. If you follow that across, you would get the energy released when the bond formed, the bond energy. So for this hydrogen-hydrogen bond, about, 450 kilojoules would have been released. That would have been the bond energy. Okay, so this question 5 is a little bit of a stinker. And we haven't done a lot with Lewis dot structures yet, but that'll come, and that would help with a question kind of similar to this. So we've got 3 graphs, x2, y2, and z2, and they tell us that they refer to hydrogen, nitrogen, and oxygen. And so we think about a couple things. I mean, obviously, like internuclear distance is going to refer to the size of the atom. The bond energy is the energy released when the bond forms, but it also kind of then refers to the amount of energy needed to break the bond. And so, first of all, I kind of like picked out the trough, the low energy level on each graph, and said, okay, I mean, x2. X2 kind of jumps out at me as distinctly having a smaller internuclear distance. The other two are kind of similar. If I follow them up to the internuclear distance, x2 is definitely smaller. Y2 and Z2 are kind of similar in internuclear distance, which must mean that their atomic radius is similar. And so right away I identified x2 as hydrogen. And hydrogen has a single bond, small atom, so that would make sense. Obviously, between these 3, hydrogen is the smallest atom. And then single bonds require the least amount of energy to break, and then they'll release the least amount of energy when they form. Making bonds, breaking bonds, same amount of energy, just different direction of energy flow. So I definitely narrowed it down then to options 1 or 2. Hydrogen's got to be x2. Okay, so then y2 and z2 must represent oxygen and nitrogen, which do have similar radii. Now, normally, I would think that oxygen would be a little bit smaller, right? I mean, if you think about trends on the periodic table, oxygen has the extra proton and the extra electron, and normally would maybe be a little bit smaller. But if I were only basing it on radius alone, then again, I would think that maybe oxygen would have a little bit smaller internuclear distance, but they're similar, and maybe they would release about the same amount of energy. And that is not the case. Y2 releases a significantly greater amount of energy when the bond forms, which would then mean that it takes a significantly greater amount of energy to break the bonds in Y2. All right, so here's what makes this one tricky, is that you got to kind of think about the single bond, double bond, triple bond. Triple bonds are insanely strong, and they require a ton of energy to break. And so between X and Y, similar radii, but the triple bond is so much stronger, it's going to pull the atoms in even closer. So, I mean, who cares that oxygen has a slightly smaller radius? It's only a double bond. And so with the nitrogen being a significantly stronger bond, and it's going to have a shorter bond length because the atoms are going to squeeze together more, Y2 is the nitrogen with the triple bond. Triple bonds are insanely strong. Lots of energy released when they form, lots of energy required to break them. So that's kind of what made this one really tricky. I think it's easy to kind of narrow it down to choices 1 or 2, that X has to be hydrogen. It's definitely a shorter bond length and definitely the smaller atom. But then Y and Z are tricky because you kind of rationalize it one of 2 ways. If you only think about radius, well, then you get it flip-flopped and you maybe picked the second option, but you have to take into consideration the fact that the triple bond is so strong. All right, so here we have a reaction that has a delta H less than 0. I don't care what the numerical value is, but if it's less than 0, that means it's negative, and delta H then is exothermic. Energy is released. This is such a fantastic question because it really gets at the heart of, like, do you understand the process of a chemical reaction, and that I've got to break all the bonds on the reactant side. That will always be endothermic. breaking bonds requires energy. Well, then I rearrange those atoms and I form new bonds on the product side. That will always be exothermic. Well, the overall delta H for the reaction is a comparison of the two. So here, if I know that overall this reaction is exothermic, then I can say that the energy absorbed as the bonds of the reactants were broken must have been less than the amount of energy released when the new bonds formed on the product side. Such a great question. Do you understand the process of breaking bonds and making bonds without having to get bogged down by calculations? Love this one. All right, so then we've got some calculations. We've got the balanced equation. I do think it helps to kind of sketch out the Lewis structures when I'm doing these bond energy calculations. And you also have to kind of be careful of the coefficients in the balanced equation. How many moles of each bond do I have? I like to sketch them out, and then sometimes I even kind of like to slash the bonds when I break them. So we got to think about what bonds are broken. Well, I've got 2 moles of hydrogen peroxide, H2O2. It's got it all sketched out. And so really then when I start thinking about what bonds are broken, I'm going to have to break 1, 2, 3, 4 hydrogen-oxygen bonds and 2 oxygen-oxygen bonds, and they are single bonds. And I have to be careful then. There were 2 moles in the balanced equation, so I think it helps to kind of just draw it twice. Then I don't forget to double it. All right, so it's going to take a little bit over 2,000 kilojoules in red to break all the bonds into 2 moles of H2O2. Then in blue, I've got all the bonds that I'm forming. So again, I'm going to kind of slash them, not that I'm breaking them, but then I know that I'm counting them all correctly. There's 2 moles of water produced. That's really going to be 1, 2, 3, 4 hydrogen-oxygen bonds. And then I've got 1 oxygen molecule, and that is a double bond. So technically, when I use these bond energies, it's like saying I would have to add about 2,300 kilojoules to break the bonds in 2 water molecules and 1 oxygen molecule. Well, I don't want to break those bonds. I want to form those bonds. So we can take the same energy value but make it negative. And so this equation is not in the AP packet. This whole bonds broken minus bonds formed. But I kind of think I know why. Because they want you to not memorize an equation, but they want you to think about the process. So here's the amount of energy that I have to add to break all the bonds on the reactant side. But then technically, if I make this negative, here's the amount of energy I'll release when the new bonds form on the product side. Making bonds and breaking bonds requires the same amount of energy. The difference is just the direction of the energy flow. Well, then the overall delta H is a comparison of these 2 quantities. And so I get a negative 203. A little bit more energy is released when the new bonds form on the product side. Sweet. This one went well. There's a little hint, I believe, in Canvas that the carbon monoxide is a triple bond. There are 2 of them. There's 1 oxygen-oxygen double bond on the reactant side, and then there's 2 carbon dioxide molecules that involve double bonds. And again, soon we'll focus more on drawing the Lewis structures and how do I know that it's a single bond or a double bond? It's coming very soon. For now, we're kind of focusing more on the bond energy. And so, again, some people just think about this equation, bonds broken minus bonds formed. It's fine, it's just not in the packet. And I think that's the why, is that we want to recognize that this process is positive, it's endothermic. This process is negative, it's exothermic. And so you can kind of think of it as a positive plus a negative. or then the minus bonds formed. And so here all I had to do is set it up. I didn't have to plug anything in. Love it. And the last couple. The enthalpy of combustion for methane. Well, number one, you better have had a 50-50 chance at getting this one right. Combustions are exothermic, right? Things are burning. So it can't be a positive value. I've never met an endothermic combustion. Things are burning. It should be exothermic. And then this one just helps to write out the balanced equation. So in a combustion, you've got your methane burning in oxygen to produce carbon dioxide and water. I've got my equation and I got it balanced. And then again, I kind of have to think about what my Lewis structures would look like and be careful of my ratios from the balanced equation. So I'm going to have to break 4 total carbon-hydrogen bonds in the methane. I've got 2 moles of oxygen, so I'm going to have to break 2 moles of O2 double bonds for a total of about 2,700 kilojoules. Then on the product side, I had 1 carbon dioxide. That'll involve 2 carbon-oxygen double bonds. And then there's 2 moles of water. Each would have 2 hydrogen-oxygen bonds for a total of 4. So again, technically, this is energy that I have to add if I'm going to break all those bonds, but I'm forming the bonds. So we're going to make it exothermic. So however you want to think about it, it's fine. I mean, you get the same answer. But I want to compare these 2 values, knowing that this now is energy absorbed, but this is energy released when the new bonds formed. So yes, it is exothermic by about 700 kilojoules per mole. And finally, this one was kind of fun. They gave you the balanced equation and the overall delta H and had you solve for a bond energy. Okay, so I kind of sketched it out. I sketched out the Lewis structures. They're all single bonds. And then set it up the best that I could. So for bonds broken, there's the 4 carbon-hydrogen bonds and the 1 chlorine-chlorine bond for a total of about 1,899 kilojoules. Then on the product side, I'm going to have to break 3 carbon-hydrogen bonds, 1 carbon-chlorine bond, and then the mystery bond. They never gave us the bond energy for HCl. Well, eventually that's what we're going to solve for, so I just set it up as X. So technically that would be the amount of energy I'd have to add to break all the bonds on the product side, but I want to form those bonds, so technically then it's energy released. So we're going to have the positive 1,899, but then I'm going to make that last quantity negative or exothermic. So you just have to be a little careful that we distribute properly now. I've got it set up and I'm going to solve for X. And the only way we can do this is that they gave us the overall delta H. So then I know that these 2 quantities should compare for a net release of 113 kilojoules. So now I just got to do a little bit of algebra, and my bond energy should end up being 431 kilojoules. And bond energy is defined as energy required to break the bond, so it should always come out to be a positive value.